verification, Genus for synthesis, and Innovus for physical level implementation up to GDSII. We have two expert panelists this afternoon. The panelist one is Dr. Hemant Kumar Mandal. He is assistant professor and PG coordinator microelectronics and VLSI, Department of Electronics and Communication Engineering, National Institute of Technology, Durgapur. He received his bachelor's degree in electronics and communication engineering from West Bengal University of Technology in 2007. He obtained his master's degree in VLSI design from Guru Gobind Singh Indraprasth University, Delhi in 2010. And his PhD degree in electronics and communication engineering from the Indraprasth Institute of Information Technology, Delhi in 2017. He was also associated with the National Center for Scientific Research, Lab STICC, UBS University in France, as a postdoctoral researcher in 2017. He is an assistant professor with the National Institute of Technology, Durgapur, West Bengal. His research interests include VLSI design, neuromorphic computing, parallel computing, energy efficient interconnect architecture for many core systems, heterogeneous system architecture, and AI infrastructure for future healthcare. He has authored 32 research articles. His Google Scholar H index is 14, and his index is 18 with 513 citations. We have panelist number 2, Dr. Rajashree Das. She is assistant professor, Department of Electronics and Computer Engineering, National Institute of Technology, Durgapur, West Bengal. She completed her PhD from the Department of Electronics and Computer Engineering, NIT Silchar, Assam. She has worked as a research associate in the Department of ECE, in Electronics and Computer Engineering, NIT Silchar, Assam, and principal engineer in Global Foundries Semiconductor Industries, Bangalore, Karnataka. Currently, she is working as assistant professor in the Department of Electronics and Computer Engineering, NIT Durgapur, West Bengal. She has several journal publications and is proficient in handling different software tools. This afternoon, this webinar will be moderated by none other than our dear Chanchal Chakraborty. He is the convener, Electronics Engineering Division Subcommittee with Bengal State Center IEI. Chanchal is BE MBA, has more than 35 years of professional experience in telecom and IT. He worked with flagship companies like CSC, NTPC, BSNL, and worked as Chief Technology Officer and Vice President in Aircel, Uninor, and Reliance Jio. He has wide experience in planning, design, procurement, installation, and maintenance in all fields of telecom. Currently, he is working as a CEO of ATM Towers India Private Limited, which is a Denmark-based company. Participated in several national international seminars, including GSM Congress at Cannes, France, Berg for International Roaming. He has received different accolades, including Bishish Sanchar Seva Award from the Ministry of Communications. Professionally affiliated with IEI, he is FIE, Fellow of Institute of Engineers. He is the Secretary, Kolkata section of International Society of Automation, USA, a team player and love to serve society to the best of his ability. So I wish our participants, our experts, and our moderator a pleasant afternoon. Let's start the webinar. Chanchal, over to you.
Thank you, Ramda. In the today's is very interesting session. Today we'll be having the very interesting topic like the VLSI and its emergence. Dr. Hemant Kumar Mandal will be talking about the VLSI perspective and how it is getting modified from the generations to generations. And Dr. Rajashree Das will be talking about the emergence of FinFET. So considering all these things, let us now start today's sessions. Over to Dr. Mandal.
Thank you, sir, for the nice introduction. And now I would like to share my PPT. Okay. Okay. Is it visible to all of you?
Yeah.
Yeah.
So thank you all. Good afternoon. So today's basically topic is very interesting and one of the most hottest topic nowadays in industry also. So how we can design a VLSI chip and whatever the flow and what are the skill sets are required and what are the future of VLSI industry in India. I'm going to discuss about through this session. Now, so before going to detail of this topic, I'd like to share some important information, specifically for students, those who are attending these sessions. So first of all, what's wrong with basically India's engineers? So first quotation is basically as many as 97% of graduating engineers wants job either in software or core engineering domain. But only 3% have suitable skills to be employed in software or product market, and only 7% can handle core engineering tasks. So frankly speaking, it is very pathetic situation. Although another quotation is graduates are collecting their degrees despite not being skilled enough to be a productive part of the Indian economy. So every year, if we notice, around 15 lakhs graduates are collecting basically their degrees, but all are expecting a good job, but at the end, as a consequence, the lack of knowledge or skill sets, so many are basically are becoming unemployed. So that's a very pathetic situation is going on in industry. But today's as there is a shortage of VLSI chip presently in industry, so that's why there is a high demand for VLSI engineers. If you know something about VLSI, and they are basically they are hiring you and they are giving proper training during internship and they are absorbing finally. But in future, so it is an alarming situation for all graduates engineers, those who are basically not serious about their curriculum and not serious about their skill sets. So for them, these quotations are very important. Now India's VLSI industry on the right track for growth. As you already aware about that, in December 2021, India announced its roughly $10 billion scheme for the semiconductor industry in collaboration with US. Now India it is expecting that 70 to 80 billion dollars maybe increase in this sector, semiconductor sector by 2026, for with the growing demand for digital devices and electronic products. And also India's shares of global economic manufacturing will rise to about 10% in next 4 to 5 years, and which is current value is approximate 3.5%. And the worldwide semiconductor industry is currently valued at around 500 to 600 billion, but electronics industry it's about $3 trillion. Now imagine how much means growing rate of this industry. And good news is that the multiple companies they are willing to set up their fabrication lab in India, including TSMC. They want to move their fab unit from different country to they want to move in India. So that is one good thing and on best thing for Indian economy also, and VLSI design engineers also. Now only we have so far in India one fab lab, that is SCL Chandigarh. Okay, if you want to know more detail about it, please go through this link. Now I just want to discuss or tell you about what is basically VLSI design. So VLSI design is a process, or technology is a process to producing an integrated circuit or to creating an integrated circuit. And it is mostly widely used for different technology for processor design, various IC design or component designs. Now, what do you mean IC? IC is nothing but if you combine thousands of transistors or gate into single silicon die, it is called IC. Now it is more than 10 lakhs transistors or more in a single silicon die. Now, what is the classification, or you can, in short, we can say that IC density of integration. So earlier it was not VLSI. So earlier term was basically SSI. SSI, then next MSI, then LSI, then VLSI, then ULSI, then GSI. And this category or classification based on number of gates per IC. In case of SSI, for example, logic gates, if number of logic gates less than 10 per IC, it is under SSI. MSI, if it is less than 10 to 100 gates per IC, it is under MSI. For example, adder, flip-flop, marks design. LSI, large scale integration, small memory chip or programmable device design. It is gate count is approximate 100 to 10,000. And VLSI basically is a very large scale integration, and count is basically 10,000 to 1 lakh. And next one is ULSI, that is, for example, microprocessor, 8-bit or 16-bit. It is more than 1 lakh to 10 lakhs. And last classification is giga scale integration. That's, for example, Pentium 4 processor. It is more than 10 lakhs, 10 gates per IC. Now, although these are the classifications, but industry also, VLSI term is very popular nowadays. So although they are following different number of gates per IC, but still we are using VLSI industry or VLSI chip. Okay, because it's already VLSI term has become a very popular. Now, for example, as I have mentioned that in case of SSI, so for example, 74 IC number 7408, it's an example of SSI category. Or 7474 D flip-flop IC, it is example of MSI category. And there is a small memory that is under LSI. And it's a very, if chip consists of more than like 10,000 to 1 lakh 10 gates per IC, that is under VLSI. And this is the example of basically ULSI. And Pentium 4 processor, it's the example of GSI. So these are the different ICs under different scaling integration in terms of number of gates per IC. Now, in case of the VLSI design, there are three types of design techniques or designs. One is analog IC design, second one is digital IC design, and third one is mixed signal IC design. So analog IC design means basically it handles basically continuous signal. And applications are various applications: audio, radio, communication, medical, electronics, instrumentation, control. These are the applications of analog IC design. Digital IC design, the applications are like most modern computers like digital cell phone, digital clock, robotics, and mixed signal like smartphone, set-top box, and there are several applications are there. Now, VLSI designs can be divided into three broad categories. One is analog IC, second one is digital IC, third one is mixed signal IC. Now, on the other end, the VLSI design technique or design flow, there are basically two types. One is full custom, second one is semi-custom. Full custom means you have to design everything from the class. And semi-custom means you will design something and you will rest of the part if it is available in the standard cell library, you will use them for your design. So today's session basically I'll talk about the semi-custom design or ASIC design. Okay. So now these are the examples of these ICs are example of, first one is example of analog IC, second one is example of digital IC, and third one is example of mixed signal. Mixed signal means it's a combination of analog IC as well as digital IC, or analog design as well as digital design. Means and this mixed signal IC design, for mixed signal IC design, you have to adopt both design flow, full custom as well as semi-custom. Now, today's agenda. So agenda for today, first I'll talk about need of VLSI chips. Then next I'll talk about skills required for a VLSI engineer. Then little bit I talk about the semi-custom design flow with example. And also I'll talk about the EDA tools, another important thing in VLSI domain, EDA tools. Okay. Then I'll show you one live demo video in our lab. We have captured from our lab, that is 90 seconds. Then CMOS process flow very briefly. Then I'll talk about simulation and emulation frameworks, open source primarily. So because EDA tools are very costly, it's around 12 to 15 lakhs. So it is not affordable for all the institute. So for them, I'll show some tools so that if they can design VLSI chip using open source EDA tools. And also I'll talk about some upcoming or emerging or ongoing technologies. Now, so why VLSI chip? So why VLSI chip? There are several applications, you know, applications such as scientific applications, astrophysics, weather prediction, then multimedia applications, biomedical application, bioinformatics application, consumer electronics, cloud computing, and multimedia applications. And apart from this, exascale computing, defense, security, medical, IoT, AI, data center, neuromorphic. So there are several applications. Okay, there are several applications, high volume applications are there. Now, for example, in case of data center application, so this first figure or top right corner figure is basically Facebook data center, and bottom one is from basically Google data center. So every day, basically we are serving Facebook, Instagram, and WhatsApp, various social apps. Okay, for each and every app will generate basically huge amount of data. That data needs to be stored somewhere, and that somewhere is nothing but a data center. And to set up a data center, we need a VLSI chip. So we can say that simply. So almost all digital systems today are based on basically VLSI chips. So that's a why VLSI. So there are several real applications where we can apply or VLSI chip is required. Now, what are the skill sets required for a VLSI engineers? So first thing is basic knowledge of CMOS circuit design, sound knowledge of, if you are looking for digital IC design, then digital electronics. If you're looking for analog IC design domain, then analog electronics. If you are looking for basically mixed signal IC domain, then you must have idea of both analog as well as digital. Then it is preferable if you have knowledge of computer architecture, because if you don't have knowledge of computer architecture, really it is very difficult to understand the VLSI processor design and everything. So it is recommended. And for design engineers, basically we need, there are a couple of two types of hardware description language so that we can design the hardware. That is, one is VHDL, second one is Verilog. So most of the industry, they prefer Verilog. And for verification engineer, we need UVM, universal verification methodology, and system Verilog concept or knowledge. And programming language, C or Java. So it's not necessary that semiconductor VLSI industry means you must have idea about the HDL language. So there are, because today's or next generation chip or today's chip will be based on, or next generation chip will be based on hardware software co-design. Some part will be designed by software, some part will be designed by hardware. And because if you are getting benefit from software, then industry that particular portion will be implemented by the software. If you are getting benefit from hardware, then that part will be implemented by the hardware. So there is a similar scope in case of software engineer also. Okay, in VLSI industry. And emulation platform, it is preferable if you have knowledge about whatever you have designed. If you want to do it hardware level realization, then you need a platform. So that platform is nothing but a field programmable gate array or FPGA. Okay, your design can be realized into hardware level. That thing can be possible with the help of FPGA. Okay, The now scripting language, so most of the industry they prefer. You must have knowledge about one scripting language, either Perl or Python or TCL. And this is obvious thing. So lots of feedbacks we are receiving from industry that student lack of knowledge about Linux command. So you must have sound knowledge about Linux command. And EDA tools, either you can explore Cadence tool based on your availability in your lab, or Synopsys, or Mentor Graphics, or Xilinx. Okay, so most for front-end design part, Synopsys tool is preferable, and back-end design part, Cadence tool is preferable. Okay, and as one important thing I would like to tell you that so Vlsi, it's all about more than 80% time you have to devote in your lab session or lab during for lab session, and rest 20% you can devote to learn the theory part. So every day you have to do practice. Okay. So now, so there are basically different types of technical fields in Vlsi domain. So let me tell you very briefly. First one is design. So it broadly 3 or 4 categories: design, EDA, manufacturing, and semiconductor research. So under design tab, basically logic design, static timing analysis design engineer, physical design engineer, standard cell design engineer, verification, DFT, and IO design engineer. And EDA tools, you can develop the EDA tool, or you can modify, or you can add some features. Methodology development, application engineers. Application engineer, basically you have to contact with the design engineer based on their target application. You have to modify the EDA tool. Product engineer and validation engineer. Manufacturing, so this thing you can say that before the fabrication, before the whatever things are required, and these are the basically part of the design cycle. Okay. And manufacturing, so manufacturing basically post silicon validation engineer, test engineer, AT engineers, and there are a couple of posters there. And last one is semiconductor research. If you have already done PhD in Vlsi domain, so you can join R&D section in the any semiconductor industry, and you can do research on it. Okay. So broadly, Vlsi industry are the main technical fields are design, EDA tools, manufacturing, and semiconductor research. Now, as I have mentioned that Vlsi design, there are two types of design techniques. One is semi-custom, second one is full custom. When we should go for full custom? Whenever we'll design the analog IC, whenever we'll design for the IO, whenever we'll design for the memory, we must go for the standard cell library, which we must go for the full custom design flow. And when we should go for the semi-custom design flow, so whenever you are designing basically digital IC, then you must go for the semi-custom design flow. So now let's start about some basics of basically system on chip. Then I'll talk about the semi-custom design flow. So these are the discrete devices. Okay, already we know. Now if we combine these discrete devices, we can make a few. We can design a logic gates are in the form of ICs. Okay. So if we combine the logic gates, we can form a large block of embedded into single IC in terms of adder, mux, flip-flop, PLL, and so on. If we combine the large block, we can for the large function into single IC like microprocessor, microcontroller, analog chip, memory element, main memory, and so on. Now, so if we combine everything inside the single chip, it is called system on chip. Means whole chip will act as a system. That is called system on chip. Okay. So as memory and main memory is always usually keep it outside the chip because it takes high amount of area. So it is very difficult to accommodate the main memory inside the chip. Okay. So based on 2D technology. Now research is going on 3D technology. Maybe we can accommodate the main memory also inside the chip. Now, how we can achieve it? So that is so we can achieve it if we follow the semi-custom design flow properly. We can design a SoC in our lab. Now, before that, you heard about the technology node. What do you mean the technology node? So technology nodes are there are basically three or four or three different regions are there. One is submicron region. Second one is deep submicron region. Third one is ultra deep submicron region. So submicron region means if you are working on a more than 100 nanometer technology node, that is under submicron region. If you are working at less than 100 nanometer technology node, it is under deep submicron. If you are working at less than 20 nanometer technology node, it is ultra deep submicron region. Now, lots of research is going on at 2 nanometer, 1 nanometer, and 0.5 nanometer. So they have IBM and Intel, they have already started work on it. Okay. And these 8 nanometer chip now they're in production. If you check your smartphone spec, you will be able to see that there's a Snapdragon or Qualcomm Snapdragon processor. It is based on the 8 nanometer FinFET technology. Okay. Now let me tell you briefly what is technology node. Okay. So technology node basically, so suppose this is a diagram of a NMOS transistor. NMOS transistor, there are 4 terminals: source, gate, and drain, and body. Okay, or bulk. Now distance between gate, source, and drain is called basically channel. Okay, and this channel is basically depends on the length of the channels. It depends on the particular technology node. For example, if you are designing your chip or something you want to design at 90 nanometer technology node, that means the distance between source and drain is 90 nanometer. Means it's all about the feature size or transistor size. So transistor size depends on the technology node. If the technology node will reduce, then transistor size will reduce. So we can accommodate more number of chips, more number of features inside the chip within the same die area. Okay, so this is one thing, and we will get the 2 types of benefits. One is speed, another one is power dissipation. Okay, so power dissipation will reduce because based on the technology node, supply voltage will reduce. Fine. So now how small we can go? So now we are in the so this plot basically shows number of transistors per die. Okay, so now we are here 2022. So here still we are using CMOS technology. But in future we don't know what will happen. In fact, lots of research and lots of conference and lots of symposium is organizing what will happen if beyond what technology industry will adopt beyond CMOS technology, because CMOS technology is very cheap, easily available. Okay, so overall chip fabrication cost is much less. Now maybe in future, maybe now they are moving basically 2D to 3D technology node. In future, maybe they can adopt the optical or photonics type of technology, but it is under basically R&D phase. Okay. So let's talk about semi-custom design flow. So semi-custom design flow basically, first you must have a target applications. So based on your target application, you have to define the specification. Specification, what does it mean? Specification means what should be the power, what should be the area, what should be the speed, and what should be the number of IO pins, what should be the supporting features. These will be under specification. And based on the specification, you have to design, you have to select the architecture. Now, next step is once based on your application, you have already specified the specification. Now, next step is RTL coding. Means you have to design it, or soft coding or soft IP. Okay. So these are this snapshot is nothing but a example of RTL coding. Okay. So now now once you have done RTL coding, then you have to do the functional verification. You have to perform functional verification. Whether your design is functionally correct, whether you are getting expected outcome or not, that thing you have to verify. So once your design has been verified, that is functionally correct, the next step is synthesis. Synthesis means the RTL phase, we have not included any technology node. So that was technology independent. Now during synthesis will include couple of technology files. Okay. Now your soft IP will be converted into the hard IP or hardware. Means your RTL code will be converted into gate level or hardware level. This process is called basically synthesis. And outcome and output of the synthesis process is called gate level netlist. Gate level netlist. Okay. So once you have done the synthesis, then you have to another step is there, that is hands-off check. Hands-off check means you have RTL code, you have synthesized RTL code, okay, or the gate level netlist. You have to compare them whether before the synthesis or after the synthesis your design is functionally correct or not, or your design is as per your specification or not. So that thing you have to verify through this step, and that step is called hands-off checks. Now timing analysis and correction. So one of the famous timing analysis is static timing analysis. So static timing analysis will ensure your, suppose you want that your laptop or mobile phone should run at 2 gigahertz. That thing you have to ensure, or that thing you can ensure with the help of this step, that is static timing analysis. Okay, means your system performance, your design performance will be verified through this static timing analysis, whether you will be able to achieve that speed or not. Okay, that thing is called timing analysis. So up to this is called front-end design. Now I'm discussing about, I'll discuss about the back-end design or physical level design. So under physical level design, there is a 3 major steps are there: floor planning, placement, and routing. Okay, so based on your design, you have to plan your basically plan your chip area properly, like building a house. Okay, whenever we build a house, we must have planned that this portion should be bedroom, this portion should be dining place, this portion should be kitchen. So like this type of planning we have to do here. So once you have done floor planning, now you have to place your, because you have already generated your RTL code has been mapped with the basically standard cell or gate level. You have already generated gate level design or standard cell based design or gate level netlist. Now your design you have to place as per your floor plan. So that is part of placement. So under physical level, first you have to do floor planning. Then once floor planning is done, then you have to go for the placement. Okay. So once placement and floor planning done, then another thing is important, that is clock tree insertion. So you have to ensure you have to distribute your clock signal to all the required components. Okay. So that process is called clock tree synthesis. Once it is done, then final step is routing. Okay, so you have to connect all the blocks as per your requirements. So final step is routing. So once routing has been done, then you have to do the post validation. Post validation means your whole design is as per specification or not, or as per your requirement or not. If not, then again you have to redesign many things. So most beautiful thing is in this domain, in case of Vlsi domain, everything is, most of the things are automated, or it is controlled by the EDA tools. So as a design engineers, you have to run couple of script. You have to run couple of script, and EDA tool will automatically perform as per your requirement. So most of the things are automated in case of ASIC design flow. So semi-custom design flow is nothing but a ASIC design flow. Now, once you have done, then you have to generate couple of files. Okay, and those files, and final file would be the GDS2 file. And this GDS2 file, you have to send it to the fabrication lab. Now, design part is over, front end plus back end. Now, output from the design end is GDS2 file. GDS2 files is nothing but it's all about, it's a binary format file. It's all about your circuit informations, layout and data and all the information. GDS2 file consists of all the information about your circuits. Okay, so you have to send your GDS2 file to the fabrication lab for final data. At the fabrication lab, you have to follow the couple of steps. I'll tell you very briefly. Okay, so then after that final chip will be tape out. So RTL, so title was Vlsi chip design RTL to GDS2 flow. So RTL coding, so here we have done RTL coding, right? RTL means register transfer level. So means signals will flow one register to another register. So that's why it is called RTL coding or nothing but. And outcome, so at the output file from the basically design cycle is called GDS2 file. GDS means graphic data stream, and 2 means it's a version. Earlier it was GDS, then GDS1, then GDS2. Okay, it's a nothing but it's all about your circuit information. You have to send it to the fabrication lab. Okay. Now let's talk about little bit EDA tools. So EDA tools are basically for analog part. So flow is idea, specification, RTL coding, gate level netlist, physical implementation, GDS2, then chip. So for analog IC design, you have to design schematic. Schematic means transistor level implementation, and that you can do with the help of schematic capture from the cadence, simulation by Spectra, layout by Virtuoso, and you have to check the DRC, LPS, and RC extraction by Asura. So this is the part of analog IC design. And for digital, there are two tools are available, or multiple tools are available. Out of them, these two tools are famous: EDA tool Cadence and Synopsys. So Cadence tool basically Insys, Genus, and Innovas, and Synopsys tool VCS, DC, Primetime, and IC. These are the tools are required for digital IC design. So I'll tell you again in next slide in a short while. So for functional verification, mainly if you want to use Cadence tool, then Cadence Insys. For logic synthesis, Cadence Genus. Static time analysis, Cadence Tempest. Logic equivalence check, Cadence Conformal. DFT synthesis, ATPG, Cadence Modas. Physical design, Cadence Innovas. Physical verification, Cadence Voltas. And DRC antenna checks, Mentor graphics calibrate. And similarly, we can use Synopsys tool also. For functional verification, Synopsys VCS Max. Logic synthesis, Synopsys DC or design compiler. Static time analysis, Synopsys Primetime. Logic equivalence check, Synopsys Formality. Then DFT or TPG, Tetramax. Physical design, ICC. Physical verification, ICC validator. These are from the Synopsys tool. So most of the industry, they prefer Synopsys tool for the front end design and Cadence tool for the back end design. Now I'll show you one example of what we have we generally do in our lab, VLSI design. So suppose you want to design a processor. Okay, so same thing you have to follow, and you want to perform different types of arithmetic and logical operation. Okay, so same thing, same ASIC design flow you have to follow. So first is functional verification. You have to open Nclone sim or Insys tool. Then you can do the functional verification. Okay, suppose this is the example of counter 0, 1, 2, 3, and so on. Means counter is functioning as per your expectation. And you can generate the report, and you can generate the report in terms of addition operation or odd operation or logical and arithmetic operation. For different types of logical and arithmetic operation, you can generate the report, and you can observe the report whether your processor is able to you're getting correct value or not. This is part of functional verification. Then logic synthesis means you can generate whatever you have written in the form of RTL code. You can generate, you can convert into the gate level and or hardware level. That process is called synthesis, and you can generate the schematic also here also. And after synthesis, you can do the static timing analysis, whether there is a slack. I'm not going to discuss about detail about static timing analysis. So whether there is any issue with timing analysis, setup time or hold time, you have to see the slack. Slack is positive or negative. If it is positive, you can go ahead. Then area, how much area it is taking. So area you can see from here. So 863787 micrometer square. This processor will consume, and total power it will consume, like this amount of power it will consume. Dynamic power and leakage power, total power, this amount of this processor will consume this amount of nanowatt power. This type of report you can generate. Now you have to verify whether reports are basically as per your specification or not. If not, then again you have to redesign. Then physical level design, you have to do some floor planning. Based on that, you have to place your design. Okay. Then after that, you have to do clock tree synthesis and routing. And final, after that, you can generate the GDS2 file. Okay, or from the final layout. This is the whole design after the physical level. And final report you can generate. And once you have already generated a GDS2 file, and this file you can send it to the fabrication lab. Now I'll show basically what will happen in case of fabrication lab. So there is a small video, same thing. Okay, I want to show 90-second video. So one of our Vlsi students, so he's designing basically MIPS processor, and he is performing different types of logical and arithmetic operation by following the functional verification, synthesis, and physical level implementations. So once you have done basically physical level implementation, now you can generate the basically GDS2 file for final tape out. Okay. Now next continue. Okay. Okay. Now CMOS. Let's tell about briefly. Let's talk about CMOS process flow briefly. Okay. So we have from the design cycle we have generated GDS2 file. So this GDS2 file we have to send it to the fabrication lab. So input of the fabrication lab is basically nothing but a GDS2 file, and output from the physically fabrication lab final chip. Okay, so in between there are a couple of activities are involved. So those activities are basically means this thing you can do this type of fabrication lab. So fabrication lab basically is a huge factory. So contain clean room as large as football field. Okay, so here you have to follow the couple of steps. Means fabrication engineer will follow the couple of steps. All are computerized and automated. So first thing is wafer production. Means this type of wafer you have to produce. Then for that there is a process, epitaxial growth. Then second step is masking. Means photolithography. So masking is nothing but a kind of printer, photo printer. Means you are keeping masking plate like this. Your design will be here, and UV light will be exposed, and and at the top downside there is a silicon wafer will be there. So whatever as per your marks, so same thing will be replicated on the top of the silicon wafer. So this is called basically photolithography or masking. Then additional thing you can remove, those are not required. That process is called etching. And for to alter the electrical characteristics of the silicon, we have to add some dopants. Okay, so either based on p type or n type. That process is called doping. Now after, so the doping you can perform by following the atomic diffusion or ion implantation. There are two processes are there. Okay, and then finally you have to do the connectivity, interconnects you can do with the help of metallization. Once these steps are complete, then assembly and packaging. So each of the wafer contains hundreds of chips. Then you have to use basically diamond saw to cut the wafer into single chips. Then diamond tip tool is used to cut the lines through the rectangular grid and separate the individual chips. And chips are basically, those are failed in electrical test will be discarded. And before packaging, remaining chips are observed under microscope or testing will take place. And last step is good chip is then mounted into the package, and then it will be shipped to the customer. Okay, through the plastic bag, static plastic bag. And there is a small video of this process. I just want to show you for 2 minutes. This is a fabrication lab from TSMC. This is the wafer. You have to maintain cleanness. This is the wafer.
The video is not coming.
What's that?
Video is not getting displayed.
A video is not visible.
Yeah.
Oh, sorry.
Silicon wafers that meet the requirements for practice a system of electronic components and circuits miniaturized onto a silicon chip 1 centimeter square or smaller.
This is wafer.
Surface is actually stacked with many components of different heights and shapes. The base of the raw material characteristics of the wafer are changed.
Ion implantation.
Silicon wafers that meet the requirements for cooking until silicon is pulled out. The outer surface of the silicon now use this set of design systems.
Polishing your design. So you have sent your GDS2 file, okay, to the fabrication lab. Then same thing will be replicated on the top of the silicon wafer, and that process is called photomasking. These are the ion implantation step again. Photolithography, etching.
So that they can perform and etched to remove uses mechanical these chips. Finally, these chips must pass the acceptance test. After passing basic inspection, throughout the entire bank, the operator usually struts wafers made by automatic material handling systems. TSMC leads the founders everything from wafer transportation to engineering.
So this is the small video from basically to understand the basic design flow at the fabrication lab. So now next one is I just want to mention some open source EDA platforms so that you can design your chip, whatever idea or into hardware level with the help of EDA tools, open source EDA tools. Okay, so like iVerilog, Xilinx Vipato, and QFlow, and for emulation, whether your idea exactly it is realizable at the hardware level or not. That thing you can verify with the help of the FPGA board. Okay, and this link is for to learn the HDL language, and using open source EDA tools, you can design this type of
You have to go back to your presentation, sir.
Okay. Now it is visible.
Yeah.
So there are a couple of basically open source EDA tools are available. You can design by yourself from your home or lab. Okay. So this for first one is these are the for simulation, and these tools are for basically emulation purpose. Now, if you want to learn HDL coding, so there is a link, so you can explore. Okay, and with the help of this type of open source EDA platform, you can fabricate your own design through eFabless Lab with some certain minimum cost. Okay, so Raven X5 processor was developed and tested with the help of basically EDA, open source EDA tools. Okay. Second thing is basically a parallel to FinFET, maybe in next generation chip or new, and now also currently working on stacked FOX-seed or nano-seed transistors. Earlier it was planar, then FinFET, then GA, gate all around. So Rajashree madam will talk about more about FinFET. Now after that nano-seed transistor, then FOX-seed transistors. Okay. So currently lots of research is going on in this domain. An upcoming and ongoing technology, there is in-memory computation or parsing in memory, neuromorphic or hyperdimensional computing platform for high-performance computing, and hardware level implementation of MLDL or AI applications, and emerging interconnect architecture for next generation SoC. So this is another important area. And industry, they are moving basically 2D technology to 3D technology for to speed up the operation and to accommodate more number of chip within the same die area, more number of features. These are the some emerging technology. So again, Rajashree madam will talk about it because I'm running out of time. So these are the most couple of important links I'm providing for you. That is, first one is international say technology roadmap for semiconductor, and this link is for best processor for designers. This link is for computer architecture to learn, and why India is building a mega semiconductor fab facility and the future of semiconductor industry. Thank you. So now, please, if you have any question, please feel free to ask.
Dr. Mondal will take the questions part at the end.
Okay, sir.
Now I'll invite Dr. Rajashree to please make her presentation.
Okay, sir.
Right. Thanks.
Rajashree, please press Control L. Control L, or there is a view option, full screen.
hear me? Visible to all of you?
Joel, can you share the PPTs? Do you
No,
have the copy?
because I
No,
have
no.
shared. I have shared, but
No, no,
I
Pages are moving, I think. The pages are
Ah.
moving, right?
yeah, Rajshri.
Sanju, can you
What?
try from your end?
Yeah, Rajshri. Do you have the this one in the PPT form? This is itself, I think it's in the PDF format.
it is a PDF format, sir.
Right. Don't you have the PPT, original PPT, not PPT format?
Yes, I have.
Better you play that.
Okay.
Now you go to the full
The
screen,
presentation mode.
Yeah.
to the presentation one. Come to the below. Yeah. Right. Right.
Is it visible now?
Yeah. Yes.
Okay. Okay. Good evening to all of you, and thank you. First of all, thank you to everyone for giving me this opportunity to deliver a talk in this platform. And first of all, today here I am going to talk about why FinFET came into the existence in a semiconductor industry. Okay, and what is it, and why it is a turning point of VLSI nowadays in a semiconductor industry. So VLSI and its impact. If we see our surroundings, we observe that most of the things are associated with the VLSI technology. So it is the technology which brought tremendous benefits to our day-to-day life. Like if we see the example, the mostly used device in our day-to-day life is like a mobile phone, right? Now in a mobile, without mobile phone, the smartphones, we are not able to communicate to each other. So the graphic cards, the chips, whatever we use in mobile phones, in a smartphones, they are nothing but the VLSI real applications. Like the smart watches, the smart gauges is everything. The smart watches in smartwatches are nothing but the VLSI applications, because now by now using the smartwatches we can receive the phone, we can call anyone, or we can measure any health related parameters, but without using any health related or medical related any parameters, right? So it is nothing but the one of the VLSI real applications in case in the perspective of medical. And also the processors whatever used in PCs are nothing but the VLSI, without microprocessor, because without microprocessors the PCs will not work. So the microprocessors are nothing but the VLSI real applications. So these are the some of the applications from the electronic perspective. In automobile industry also, the VLSI has shown its utility as processors. So there are so many areas where VLSI shown its tremendous benefits, and Hemant sir also has already explained its different areas, the VLSI and in its uses in various areas, including this electronic industry, and also the automobile industry, the medicals, and everywhere is now in a VLSI. Okay, now the demands of the semiconductor industry. Uh, so based on the uses of the VLSI real applications, whatever the uses we now use in our day-to-day life. So based on that, the semiconductor industry now in a run to fulfill the demands of the present condition. So we as a customer, what we want a portable device, the device which have a very low weight, as low weight as possible. That means it can be carried very easily. It should have a high quality, should get in a lesser cost, in small size, can operate more functions, less heating effect, and get at less cost. So based on the customer needs, an employer should design, or the aim of the employer should be like to design an IC with a better specification, okay, to be the best with lower cost and be get in a lesser time. Now the based on these demands and all the demands, keeping in mind what the chief designer will do, it will he the chief designer will design chip, like design a chip with a high speed, should occupy the smaller area, should have the low power, it should be reliable and stable. So these all these demands are now in a semiconductor industry. Okay, a chip be a reliable or stable. That means reliable. That means that the device should not be affected by any external undesired effects, and maintains the electrostatic integrity. And stable means when a device works in a high temperature, or placed in a high temperature above the room temperature, the device um, should work properly without hampering any electrostatic integrity. Okay. Now the question is how it is possible. That is, how can a device will be more functionable with high portability? Okay. So the answer is this is happened due to the scaling of a transistor. Okay. Here we can see from the graph that we can observe that how much transistors can be incorporated till here. I have here it is shown up to the 2007. Okay, here we can see the lots of transistors are incorporated in a single IC. From here it is sent from the 1970, here the 2500 transistors, and here in a 2000 after 2007 it is 1 billion of transistors. Okay. So in the era of 1960 to the around of 1985, the bipolar devices, PMOS devices, and MOS devices are used in an IC, where the technology node used was 10 micrometer. From 1985 to around 2015, the further scaling down occurs to get the more functionality, to get high portability, to get in lesser cost. The more scaling down occurs, and worked in a technology or in a 100 nanometer to 10 previously it was in a 10 micrometer, then it was scaled down to 1 micrometer from 1985 to around 2015. 10 micrometer, 1 micrometer, then 100 nanometer, then 10 nanometer. In this era, here from 1985 to 2015, there are voltage scaling also occurred, power efficient scaling was also done, and CMOS device was used as a transistor. Okay, but after 2015, what is next? Beyond 10 nanometer, because after 2015, the 10 nanometer has been used in a device as a device. So after 2015, what is next? Beyond 10 nanometer, beyond CMOS, what is next? because the further scaling down of the device dimension causes the short channel effects. Okay, so various scaling down of device dimension, because further scaling down occurs. So further scaling down occurs, which causes the various short channel effects. Short channel effects are nothing but as the channel length is scaled down to first it was 10 micrometer, then 1 micrometer, to 100, then 10. That is the channel length has also cut down. So due to this channel length to cut down, the control over the control of the gate over the channel is now reduced. Okay, the MOSFET structure has already shown by Hemant sir. So from there also we can understand that when the channel has been shortened, the chairs in the channel has been shared now in between the source channel and the drain channel junction. Now the control of the gate over the channel is now reduced, and the control is now shared in between the source and the drain. So as a result, we will get not only the drain current, we will also get some amount of the leakage current, some amount of the body current. Okay, so this is nothing but the short channel effects. So this is called about this phenomenon is nothing but the short channel effects. And due to this short channel effects, there are various short channel effects has been occurred, like drain induced barrier lowering, threshold voltage roll off, mobility degradation, etc., etc. So these are some of the points of the short channel effects. Less on drain current. Less on drain current, that means at gate voltage like 1.5 or 1.2, we will not get that much of saturation drain current, and because of this short channel effects, the on drain current will be less. High of current, that means when the gate voltage is zero, no gate voltage is applied, that time also we will get some amount of current. That current is not required by us. That current is called is nothing but the off current. And less on current to off current ratio, because less on current to off current ratio, because of that less on drain current and high off current, we will get lesser on current to off current ratio. And the another point is we will get an enhanced gate induced drain leakage current. Gate induced drain leakage current, that means when we apply any gate voltage, we will, because of this short channel effect, we will get the body current. Because of the body current, that is nothing but because of that gate, and we will get an leakage current through the body, that is nothing but the Giddel current, which is which is also one of the short channel effects. So considering all of these effects, considering all of the effects and to overcome these drawbacks due to the scaling, the researchers have come up with some alternative devices which can replace the or may replace the CMOS devices or MOSFETs. So there are more number of alternative devices have come up, like carbon nanotube FETs, graphene FET, nanowire FET, tunnel FETs, ferroelectric FETs. So these are some of the FETs so which come up with some advantages to overcome the drawbacks caused by the source channel effects in a 10 nanometer regime. So in sub 10 nanometer regime, the CNT FETs have shown its positive growth in applications. Graphene FETs has also used, and another conventional FET which shows high carrier mobility than carbon nanotube. Nanowire FETs has also come up, where group 4 materials are used as a semiconductor material, group 3-5 compound semiconductor materials are used, but the diameter of nanowire is very thin. And then tunnel FETs have come up, which main very good advantage is that it shows the sub 60 millivolt per decade. The subthreshold swing in MOSFET is the limit is 60 millivolt per decade, but in tunnel FET we will get the less than of 60 millivolt per decade subdressal swing. That means it's a very good quality of the tunnel FETs, but it has also some disadvantages like ambipolarity and that. Ferroelectric FETs have also come up with some advantages and all that. But these devices also has some troublesome, like some has zero band gap, some has ambipolarity effects, and what and what not. So so the question, the answer of that question, that what we have arise that what is beyond the CMOS, what is beyond the 10 nanometer, what would be the device will be used in the semiconductor industry in an IC below the 10 nanometer. Okay, now the time is to emergence of a three-dimensional devices, because all the devices whatever we have discussed is nothing but the two-dimensional devices. Now the time is the emergence of a 3D devices. The FinFET, it is nothing but the FinFET, fin field effect transistor. Okay, so the FinFET is virtually replaced the MOSFET, as it is because more capable of to overcome the short channel effects which is arises due to the scaling. Why it is called FinFET? Because the shape of this geometry is nothing but the fin shape. The shape is nothing but the silicon is look like a fin. So that is why it is called fin, and the other is fin, other is FET. That FinFET is double tri-gate field effect transistor. The first coined the term by Chen Minghu, Chu Jacqueline Liu, and the Jeffrey Walker in 1998 at the University of California, Berkeley. If we see the difference between the MOSFET and the FinFET, we can observe this is a MOSFET, a FinFET structure. It's a conventional FinFET structure. No modification has been done. This is the first FinFET structure which is developed by this one. So we can see here this is a MOSFET structure. This is the gate channel length. Here the channel length is equal to the gate length. This is the oxide width of the silicon substrate. This is a source, gate, and a drain. Here is the FinFET structure. This is called nothing but the fin. Here this one and this one. Below this is also here, but it is overlapped. So this is the main advantage of the FinFET, that the oxide layer, this is the oxide layer, and the gate material straddles over the fin. This is a fin from one side of the fin to the other side of the fin. Okay, so this is the main point of the FinFET, and this which causes the more control over the channel. As the scaling down occurs, the channel the gate loses its controllability over the channel, because the channel charge is now shared by source and the drain. So this drawback is overcome by the use of the FinFET, because now the gate which straddles over the fin from one side to the other, it enhances the gate control over the channel. Now the question is, when the fin acts as a channel, because whole thing is a fin. When you apply input voltage to the gate which is occupied by the channel fin, that portion is nothing but the channel, and this is nothing but the gate electric. This is a source, this is a drain. This is the height of the fin, this is the width of the fin, this is the length of the gate or length of the channel. So this is the basic characteristics of the fin, that fin itself acts as a channel when input voltage is applied to the gate. The gate orientation is at right angles to the vertical fin. It is called vertical because it's not a planar. It's a very thin, so it is so that is why it is called a vertical. And it is right angles. The gate is right angles to the vertical fin. Okay, and it wraps over the fin and enabling it to interface with three sides of the fin or the channel. So the wrapping around nature of the gate provides the better electrical control over the channel and helps it reducing the leakage current and hence enhance the electrostatic integrity. Now, how FinFET works? What is the working principle of FinFET? The working principle of FinFET is same as the MOSFET. When input voltage gate, when positive gate voltage is applied, a depletion region is formed. When a high gate positive voltage is applied, the inversion layer is formed. And when drain voltage is applied, the drain to source current will flow from drain to source. Okay, so based on the FinFET structure, it can be classified into two main categories as a shorted gate and the independent gate. So shorted gate, that means both the front and back gates are physically isolated. So it is that is why it is called the shorted gate FinFET. From here also we can understand. This is a shorted gate FinFET. This is the independent gate FinFET, and this is asymmetric shorted gate FinFET. In shorted gate FinFET, both the gates are isolated, physically isolated. They are shorted, and a single gate supply is applied to this gate. So that is why it is called shorted gate. Independent gate, that means these two gates are individually isolated. Two different contexts are applied to two different gates. That is why it is called gate 1, gate 2. And here it is asymmetric shorted gate FinFET, because the shorted gate FinFET is further categorized into asymmetric shorted gate FinFET. If the work function of this gate and these two gates are different, then it is called the asymmetric shorted gate FinFET. But since both the gates are physically isolated here and have a one common contact, and here there are two different gates are applied, two different contacts are applied, and there are no the contact from above. So the gate control or the electrostatic nobility in case of shorted gate FinFET is more compared to that of the independent gate FinFET. To improve the functionality of the FinFET geometry and investigate the different functionality of FinFET, the FinFET geometry has been further categorized, or have been different FinFET structures have been proposed by the researchers, like double gate, tapered tri-gate, pie-shaped gate, bulk FinFET, scallop-shaped FinFET, omega shape, and cylindrical gate all around FinFET. Double gate FinFET is means there are two gates. Gate 1 means left and right. There is no top gate. Tapered tri-gate, that means the gate is looks like tapered shape. Pie shape means the FinFET, the gate of that FinFET is in pie shape, and it is a bulk technology. That means a silicon substrate is used below the fin. The silicon substrate is used. Scallop shaped FinFET, it's the gate is in scallop shape. Omega shape, that means a half spherical, and a cylindrical, that means the gate all around the FinFET structure. So FinFET basically we can design or we can simulate for the bulk technology also, or for the SOI technology also. Bulk, that means below the silicon, there are silicon substrate we will use. If we soy means silicon on insulator SOI, then we will use silicon dioxide below the here below the silicon. We will use the oxide, silicon dioxide below this fin. Then it is a soy technology, SOI, silicon on insulator. Okay, from the industry here, in industry also nowadays, in most of the smartphones, the FinFET technology is now being used. Samsung adopted the FinFET, that is 14 nm technology, 14 nm node, 14 nm technology node, now predicting the significant benefits over 20 nm. 3 nm FinFET technology is now being used by TSMC. The Apple iPhone has ordered the 3 nm FinFET chips, which is now being produced, or the chip now being generated by, or now fabricated on produced by TSMC. The 3 nm process based chip now that TSMC will ship to that of the Apple. and that iPhone, that 3nm FinFET technology that is being used in an iPhone that will launch as an iPhone 15 series, which will launch in 2023. So that is why, and also moreover, I want to let you know that the FinFET device nowadays is a very interesting topic in a research area also, research area, because everywhere we can see the FinFET is now being used in the smartphones. In the 3nm FinFET is now being used in Apple iPhone 15 series. So this is a very good topic for the research. We can simulate the FinFET device by using ticket simulator, ticket Silvaco simulator, and Synopsys Centrus ticket simulator. Okay, so it's a very good topic for the students' purpose, also for BTech project, for the MTech project, for the PhD research. Okay, and lastly, thank you.
Thanks a lot
Thank you, sir.
to Dr. Mandal
Yes,
and
sir.
to Dr. Rajashree
Yes, sir.
for the completely illuminating talk today. It has given the new dimension of thought process, because you see, from the any digital technology, whatever we utilize, it is using the chip, and without chip we cannot move anywhere, be it a handset or be the communication device, be it the IoT device or whatever it might. We are rather surrounded by this technology. So the VLSI technology is a must. I can remember my college days when you people were delivering the lectures, and not many interesting inputs have come from your lecture process. Now, if you see that what Dr. Mandal has told, I have been given the moderating this talk, and what for the students and for the learners and the audience, the VLSI is a very large scale integration. We have talked about SSI, MSI, LSI, VLSI, ULSI, and GSI, and then we talked about the analog IC applications of that, digital IC and mixed signal IC. And then we have moved further, that we have seen that the VLSI chips need any application, whether it is a scientific application, whether it is a consumer electronics, it's a cloud computing, multimedia applications, and henceforth. So almost all digital systems are today based on the VLSI chips. And now, if we go for the evolution of system on chip, we have seen that the evolution of system of chips, we have seen the adders, marks, flip-flops, and all, which were disintegrated fashion. But in SoC, we have seen everything has come together in a single chip, like the microprocessor or microcontrollers, cache RAM, SRAM, register file, ROM, etc. And main memory, of course, is kept outside. But nowadays, the research is on to integrate under the only one platform. Now we have seen when the technology shrink, the channel length, that is the distance between the drain and the source, it is on the submicron region, then to deep submicron region, and then we are going towards the ultra deep submicron region, where we are moving towards the 1 nanometer technology. It has been told that IBM, Intel, they are moving for that, and Snapdragon is utilizing the 8 nanometer technology. Now, question is, what beyond the CMOS? So, a lot of interesting articles have been told today. Now, if we see the chip design perspective, we have seen that it is starting from the blocks specification. First, we have to see the target. Based on that, the specification is obtained, and then the RTL coding is done. RTL coding is nothing but the soft coding, and from that the functional verification is happening. Then it comes from the soft to hardware. It is the basically the synthesis part, and after doing the synthesis part, the GNL is coming, because that is then the equivalence check, that is the verification of the design and synthesis part. Then we are going toward the timing analysis and correction, where basically the static timing analysis is done to see the system and performance analysis. Then we are moving to the physical level design. So far we have talked about the backward backend design, then it will be the front end design. So floor planning is done, and then the placement is made. Then the clock tree insertion is done, where the distribution of clock signal to all parts is analyzed. And then the final routing is done. And next will be the post PNR function and timing check. So at the basically the verification will be done on the entire thing with respect to the specification, whatever we have done. And once the physical design part is prepared, from that the GDS2 file is made, that is the graphic data stream, and then it is sent to the fab lab, and then from that the final chip output will be coming out. And to analyze these things, we are having EDA tools, and EDA tools will be doing all such cases. And we have also seen that you can utilize the Raven RISC-V microprocessor from eFabless. So next, whatever is happening, that from the planar's design, that is from the FinFET, the nano sheet, and then the fork sheet is getting designed. And also we have told that some ongoing and upcoming technologies are coming, which will be very much interesting part for the students and the researchers, are the in-memory computation. Then there will be neuromorphic computing platform for HPC. Then there will be the HDC, that is the hyperdimensional computing. And like that, there are a lot of these things, and it is moving towards the 3D technology. So next part, we Dr. Rajarshi Das has illuminating there. She has talked about the emergence of FinFET. Now it has come because the demands of the semiconductor industries are from the customer demand part. There will be the employer's design demand. There will be the chip designer demands, and like that it is getting. And because of the transistor is scaling down, say from 1970s till date, it is moving towards the 1 billion transistors devices. And because of the scaling down of the devices, that the device dimension, it causes basically the short channel effects. Now the short channel effects, what is happening? The control of the gate on the channel is getting reduced, and the cause is the drain and the body leakage current is getting increased. And because of that, to combat these things, there are a lot of alternative devices have come, like carbon nanotube FETs, the graphene FET, nanowire FETs, the pin diode tunnel FETs, ferroelectric FETs. Those have been devised. Now we have to think that beyond CMOS, what are the things, and the emergence of 3D devices have come as a boon towards the system. And we have seen the emergence of FinFET, the very name that it looks like fin. And in the fin structure, we have seen that how to establish the control of the gate on the FinFET architecture. And we have also seen that there are the different kinds of the structural definitions, like the SG architecture, independent gate control IG, and the asymmetric structures. So considering all these different type of fin gate geometries, we have seen that the different type of proposals in the type of structures have come, like double gate structures, tapered tri-gate structure, pie-shaped structures, scallop shape, FinFET, and omega shaped architectures. Now, with this evolution, we have seen that the Samsung is adopting the 14 nanometer FinFET technology, and Apple has come out to release their iPhone 15 series with the 3 nanometer FinFET technologies. So FinFET is giving the very much interesting applications for the different type of devices, at considering the power consumptions part, the dimension effects, and the future processing parts. So with all these things, now I will invite the audience for the questions. If you're having any questions, our experts are here. They will answer your queries. Now, the first question here, is it possible to manufacture 10 nanometer technology chip in India? Praveen Matthew has asked.
Actually, right now, it is not possible. Whatever setup we have, but in future, whenever fabrication lab will be set up either in Gujarat or Karnataka, place is not finalized yet. So that time it is possible.
Okay, thanks for your thoughtful answer. You must be knowing, the audience, that the lot of investors have come, and because of the Make in India drive, the different big houses have come for the manufacturing of the technologies. So once this type of labs will be set up by Tata Elixir, Vedantu, and all such, with the collaborations, it will be possible in near future. Now, Pramod Ranjan Depnath has asked, in today's industries are migrated from TIP to SMD version incorporating VLSI or ULSI chip, resulting which the chip and related PCBs are becoming miniature in nature. Dr. Mandal, do you want to comment on this?
Actually, sorry to say that.
Actually, based on this, actually, he has asked the question. My question is that how we are checking their reliability in rough environmental condition.
So reliability, actually, there is a different process to check the reliability during the design phase. Okay. So there is a process. That process is called PVT analysis. Okay. Process, voltage, and temperature analysis. If we perform, whenever we are moving towards ultra nanometer technology node, so earlier, whenever we were working on deep silicon technology node, that is more than 100 nanometer technology node, that time we generally avoid many such. There is no such big question about reliability. Now, whenever today's chip is fabricating at 10 nanometer, or 14 nanometer, or 8 nanometer, and 5 nanometer, that means there is a big question about reliability, right? So reliability means, so here at low nanometer technology node or ultra low nanometer technology node, so only possible thing is, as a design engineer, you have to perform process, voltage, and temperature variation during the design phase. Okay, so what does it mean? So how, if the process will vary, then what will the impact of the overall system or circuit performance? If the voltage will vary, what is the impact of the circuit performance? If temperature will vary, suppose for example minus 25 degree to plus 120 to 125 degree, then what will happen? So if you perform this PVT analysis during the design phase rigorously, so if certain or some environmental or some uncertainty will come, then there won't be any effect.
Okay, thanks, Dr. Mandal.
Is it clear to you? I think.
Thanks, Dr. Mandal. I think Mr. Debnath, you got your answer, that it has to be done based on the PVT analysis. Okay, so if you are having any further query, you can put the question over here, or you can unmute yourself and place your question. And then one question has come from Panda Srikant. His question is disadvantages of FinFET. Rajashree, it's your question.
Okay. The disadvantages of FinFET, it can say as it's a corner effect, because the fin actually it traverses from one side of the fin. Gate is traversed from one side of the fin to the other side. So the corners which is surrounded by the gate is affected, because the gate, because of that corner, there are more electric fields are generated at the corners. So because of that, some of the gate leakage current we will get. So the corner effect is one of the disadvantage of in case of a FinFET. So there is a kink effect also we have, and the swing a little bit high in compared to the MOSFET structure. Yeah, so these are the some of the disadvantages of a FinFET structure. Because
Good, that is it.
yeah, every device has some disadvantages, of course.
Yeah.
So
Very good.
actually, in
Yeah.
addition, sorry to say, in
Yeah,
addition to Rajashree ma'am, Rajashree ma'am explained it in a technical way. Okay, so I would like to add one more point. That is, there are different technology nodes like ST microelectronics. They have introduced FDSY, FinFET. Intel was introduced. Okay, now they are moving from FinFET to nanosheet or nanowire or Foxy transistor. So disadvantage means why they are moving, because when they are they are observing that if we move from one technology node to another technology node, every industry they have to invest a lot. Okay, so if we want to if we move from one technology node to another technology, or one technology to another technology, then what kind of benefit we'll get if we invest that much amount, and will get back or not? Okay, in terms of power, in terms of performance, in terms of features. So industry point of view, they're moving or they're introducing different types of technology due to their benefit in terms of power, voltage, performance, and overall cost.
Absolutely. So Dr. Mondal has briefed the entire thing. So we have seen that there is a corner effect, there will be the kink effect, and other cost benefit analysis for the investment perspective. Every industry will be seeing from that perspective. Of course, the future demands are getting increased. The technology also will be moving towards that to catch that space. Now, Mr. Suman Kalyan Porel, he has asked, how should I explain the difference between 180 nanometer CMOS process and 65 nanometer CMOS process? Over to Dr. Mondal.
So actually, 100 nanometer technology CMOS process means simple. There are difference between feature size. Okay, so feature size means the distance between source to drain. Okay, and this whatever design rules are there or layout rules are there, there is a layout rule, that is lambda rule. Okay, so lambda rules depends on feature size, and feature size depends on distance between source and drain, and distance between source and drain depends on technology node. If the technology node will change, then feature size will change. If feature size will change, lambda rule will change. Then we have to whenever we will design a layout for a particular design, we have to follow the different lambda rule for a particular technology node.
Right. So I think, Mr. Porel, you got the answer. Now, next question from Banda Srikant is how can we say CMOS is 2D and FinFET is 3D devices?
So it's not about CMOS is 2D, it's not about FinFET is 3D. So if you suppose in 2D there are XY dimension, right? Now same plane or same wafer or same layer, if we stack in a vertical way, it will become a 3D. So it's not about the technology. I think 3D can be applicable for irrespective of any technology node.
Okay, that's right. It has been briefed very well. Now, Mr. Manas Parai, he has asked, is there any open source Cadence software available?
No, my answer is no, because Cadence are these are the pioneer EDA tools. Okay, if any Cadence tools are available, and those are the pirated version, but I would recommend that don't use those Cadence tool, because you will not get full features Okay, so better to use Q flow instead of cadence. The same thing you can perform using Q flow tools instead of cadence.
Okay, Manas, I think you got the answer. Instead of cadence, you can utilize the Q flow. Okay, so now there are no other questions we are finding in the chat box. So is there any question from anybody else? They can unmute and can put the questions, because this is a very good chance that we got the two excellent speakers over here, and you can put your questions if you are having some more questions, like where it is left within yourself. One question has come from Suman. Could you explain what is sub-threshold swing?
Madam, Raishi Madam,
Yes, yes, yes.
please
Okay.
explain him.
Okay. Soft result swing, you can say it's the inverse of the slope. Okay. The amount of this is a bookish definition. I will tell you. The amount of gate voltage which is required to degrade the drain current by 1 millivolt per decade. Okay. So the swing, that means these are on to off, the duration of on current to the off current. So nothing but the swing.
Okay. Now Suman has asked another question, and why value of 60 millivolt per decade is good? Rajashree.
Okay. Why it is good? Why it is good? It is not saying that why it is good. It is already in case of a MOSFET, it is a nothing but the KT by Q value, which is the 60 millivolt per decade. It is already, it is a what you can say. Uh,
Rule
it
of
is a
thumb.
reference point.
Right.
Hmm.
So it is basically from the KT by Q, the definition itself, it
Huh.
gives the threshold value,
Threshold
right?
value, yeah.
And that
Yes.
gives the 60 millivolt per decade. So that is the threshold we need to take care of. Okay. Now, I think there is no other question. So as there is no other question, now our, I think another question has come. What is the constant clock means in Xilinx Vivado?
So constant means basically whenever you are performing any synthesis, okay, that time you have to impose, you have to give a constant file. Constant file means under this file you are restricting your design, that your design should run at a particular clock speed. Your design must have this much of uncertainty. Your design must have this much, should not exceed this much of power, should not exceed this much of area. So these type of constant you are imposing during the synthesis, so that your design outcome will become as per your specification.
Okay. As Suman has told, many thanks to sir and ma'am. We also convey the same thing from our side. Now I will invite Professor Dr. Raju Basak, our Honorary Secretary of West Bengal State Center of IEI, to give their vote of thanks.
Thank you very much, Engineer Chanchal Chakraborty, for inviting me for a vote of thanks. Is it audible?
Yes, sir.
Okay, thank you very much. So it is a proud privilege to extend my sincere thanks and gratitude to all the distinguished participants in this technical webinar on the theme VLSI, organized by the Electronics and Telecommunication Engineering Division, West Bengal State Center, IEI, through this online platform. Now, at the outset, I convey my sincere thanks to the panelists, Dr. Hemanta Kumar Mondal, Assistant Professor, PG Coordinator, Department of Electronics and Communication Engineering, National Institute of Technology, Durgapur. Dr. Rajashree Das, Assistant Professor, Department of Electronics and Communication Engineering, National Institute of Technology, Durgapur, West Bengal. My sincere thanks also goes to Dr. Nirmal Das, West Bengal State Center, IEI, Chairman of West Bengal State Center. Engineer C. Devnath, President of IEI, Professor Dr. Girish Sri Kishan Munda Dada, Chairman, Electronics and Communication Engineering Division, Board, IEI, Engineer Ramchandra Chakraborty, Joint Honorary Secretary, West Bengal State Center, IEI, Engineer Chanchal Chakraborty, Convener, ET Engineering Division, West Bengal State Center, IEI, and the moderator of this program as well. He has moderated so well every program whenever it is organized by the Electronics and Telecommunication Engineering Division. He has moderated the program very nicely. Thank you, sir. Thank you very much. The same feelings also goes to uh, all members of the council and division board member of ETDB, and all members of the committee of West Bengal State Center IEI, and all members of the ET Engineering Divisional Subcommittee, Director Technical IEI, and his team for their wholehearted support to make the program a success. Last but not the least, my sincere thanks also goes to those persons who are giving their silent support, who are standing behind the screen, and to make the program a success. Thank you very much. With this, we are concluding our today's webinar here. Thank you very much.
Thank you,
Okay,
Dr.
thank you,
Basak.
sir.
Thanks, Dr. Basak. And also, I want to extend my thanks to Dr. Mandal, who is the HOD of NIT for Electronics and Telecommunications. And whenever Dr. Durbadal Mandal, I have found whenever we are talking about this type of seminars and other CTEX active interest. So thank you, sir, for extending this facility, and it has provided us the two excellent speakers on this particular subject, Dr. Hemant Kumar Mandal and Dr. Rajarsi Das. So, I have we have met in NIT Durgapur, and
Yes,
many more things, support and other things it will be done. And also from your side, whenever this type of webinars will be coming, I think you will be joining us. So with these things, I think we can conclude, and Ramdev, I think we can close, right,
Yeah.
today's sessions.
Thank
It has
you,
been-
from my side, Professor Mondal and Professor Das,
thank you,
for
sir.
your well-illuminated presentation. I was remembering my college days way back in 1980 when Professor Yasha used to teach us circuit design. I could not find any book where from to study, and class test we were really tensed for the class test. That's very good. Thank you so much, sir, for your time.
Thank you, sir.
You shall be in touch, definitely.
Sure, sir.
Thank you very much.
Okay,
Thank
sir.
you very much. Thanks.
Okay, thank you, sir.
Okay.
Thanks
Okay.
for the audience.
Thanks for the audience. Yes, of course.
Yes, we have a very good audience today. Not many questions. 18 questions I could see, and many of them are thanks to the speakers. Will the participant get a copy of PPT? It will be uploaded, I think, already in YouTube. You can go to YouTube, and I will check with the authorities of IEI if they. I think normally they don't share the PPTs, but it is available in
It
YouTube.
will be there in the YouTube. Yes.
Yeah, it is there
Yeah, it
already
will be there.
recorded.
We'll check it. We'll check it up. And for the audience, in the next month on 24th June, we'll be making another interesting webinar on image processing and basically steganography. So that we are organizing in the next 24th June at the same time. So we'll meet till then. Goodbye and have a very pleasant evening.
Yeah, please attend our every monthly webinar, which is on the state of the art topic given by the experts from academics and industry.
Yes.
Thank you so much.
Okay,
Thank
sir.
you.
Thank you so much, sir.
Namaskar.
Thank you, sir.
Thank you.
Thank you, sir. To all the participants, here is an announcement. Our e-certification link is open till tomorrow midnight. Participants who want to obtain the e-certificates, please deposit the requisite fees, and the certificate will be forwarded by email. Thank you.
Thank you so much. Kingshuk, you can now close it.
Yes, sir. Yes, sir. Thank you.
Thank you so much for your time, Kingshuk.
Thank you, sir.